Bam, Mr. Tarrou. In this video, we are going to look at the relationship of the two-sided significance test and confidence intervals. Now, when you have a two-sided significance test, that means that H sub A, your alternative hypothesis, is going to be set up as mu or p or x is not equal to a number. And thus, for those tests, you're going to set up both the left, you're going to shade or account for the shading of both tails. Now, when you should have learned about confidence intervals, and in confidence intervals, you take a sample and you get a statistic, whether it's x bar or p hat or whatnot, and you have a sampling distribution centered around that statistic, and you set up confidence intervals based off of that to try and estimate the true population parameter. Well, if you want to be 80% confident, you're shading the inside of that bell curve and ignoring or not shading the two outside tails. So if a two-sided test is shading the outside tails and a confidence interval is the inside with those two outside tails not shaded, then there's this complementary relationship between the two. And thus, when you have a two-sided significance test, you have a choice of analyzing that through doing a t-score or a z-score, depending on what your situation is, or you can set up a confidence interval to answer the question as well. You have a choice. And these notes are going to be well, I'm going to do two examples, but the notes here are about the confidence intervals relationship between that two-sided test. So a two-sided significance test rejects the null hypothesis, H sub O, when the value of mu sub O, and that could be, so that's a population mean, that could also be P sub O, population proportion, falls outside the confidence interval whose level of confidence is the complement of alpha. Now, again, let's not forget, when we're given, if we're going to be given the population parameter, mu sub O or P sub O, or maybe X if it's binomial counts, the purpose of a confidence interval is to estimate that value. So do not make a confidence interval ever around what you're assuming to be true. You never set it around the population parameter if one is given to you. So since we're talking about significance tests, we're going to be having, we're going to have those x bars and those p hats, those sample means and sample proportions, and with a significance test, you're always assuming H sub O to be true. So we're going to have this population parameter. Make sure that you center the confidence interval around the statistic, not the parameter that you're assuming to be true, not the parameter that's commented on or referenced in your H sub O statement. That would be a huge mistake. Now, the example we're going to read here is got a level of significance of 5%. So if my p-value is 5% or less, then that's shared between the two tails, so 2.5 and 2.5%. The complement of that is 95%. So if I do a confidence interval, which I will in my first part of this example, when I set up a confidence interval, it will be the complement of alpha. It will be a 95% level of confidence, that interval. So a company claims a product contains 16 ounces of product, solids, fluids, whatever. You, as quality control, check 5 items to test if it is not 16 ounces. Now, the company doesn't want to put too much into this product. They'll lose money. They don't want to put too little in it. They'll get sued by somebody for false advertising. So they're concerned about too little or too much. And thus, you're going to be looking to make sure that that product, or looking for if that product is not 16 ounces. Remember, we are assuming H sub O to be true, but we're trying to prove that H sub A is true. We're trying to see if there's any evidence against H sub O or if there's not evidence against H sub O. So you're going to be looking for if there's not 16 ounces. You obtain an average of 15.3 from your sample. That's going to be X bar, because clearly there's not just two outcomes when you're measuring numbers of ounces, so there's no way it could be a binomial setting. And a standard deviation of 0.7. Now this is talking about your sample's standard deviation. You looked at some items and you got a mean and a standard deviation from that sample. Assuming the distribution is normal, test the company's claim at a level of significance of 5%. Now, okay, I was making sure I included the size of the sample. So we have n equals 5. We have a sample mean, a sample standard deviation, and a level of significance. Let's see what this looks like. Okay, so we have a statement. What am I going to do? I'm going to do a one sample mean t-test. I'm working with averages. I have the sample standard deviation, not a population standard deviation. So that's what I'm doing. One sample of 5 means and sample standard deviation. So that's what we're doing. You should always get in the practice. At this point, you need to get in the practice of stating what kind of test you're about to do, and then do your checks, or state your hypothesis, do your checks, and move on. So we have the company is trying to make a product with 16 ounces of whatever in it, and as quality control, we're making sure we're looking for if it's not 16 ounces, and we have the variable defined. Mu is equal to the amount of product in the items. Our conditions, our 3 rules of thumb: SRS, normality, and independence. We need to assume the 5 items chosen represent an SRS. Now for normality, I had to tell you in that setup that the distribution of the product fill rates or amounts was normal, because with a sample size of only 5, the central limit theorem is not going to have very much punch behind it to make sure that the distribution of the averaged values are normal. So normality needed to be stated with such a small sample size. Independence. It's safe to assume that more than 10 times 5, more than 10 times the sample size, that there's more than 50 items produced, otherwise we'll fail the independence check. So, since it's two-sided, and in a two-sided test, I'm going to have a drawing over here in a second, so I'm not sure I'm doing this now exactly, but again, with a two-sided test, you're concerned about, filling the areas of both tails. The complement of that is your confidence interval in the middle. So since from the previous page I said this level of significance was going to be 5%, the complement of that is 0.95. Now, let's go ahead and keep referencing this picture here. We have a sample mean of 15.3. We have a standard error of the mean, which is 0.7, the sample standard deviation, divided by square root of 5. Our degree of freedom in a t-test is n-1, so we have a sample size of 5, so a pretty small degree of freedom of only 4. And my t-star, my critical value, is 2.776. Now in a t-score chart, you're going to look at the bottom of that chart, find a confidence level of 95%, and then go up that chart until you get to a DF line of equal to 4. And there is one. That's how I got this t-star value. Again, if you have a degree of freedom that's not on your chart, you want to go up the chart. You want to use the largest degree of freedom that is smaller than your calculated degree of freedom. But we have a DF line of 4, and thus t-star is given. And how do you set up a confidence interval again? It's estimate plus or minus critical value times standard deviation of the estimate. And again, let me just reiterate, you do confidence intervals around the statistic, around the estimate. I mean, it says that on the formula sheet. That's what I'm reading basically, or verbalizing what's on the formula sheet. Do not build this around the assumed to be true population parameter. Do not build this around the 16 ounces. We're trying to test that claim, not make confidence intervals around it. So, based on this calculation, and here is again your X bar in the center of that bell curve distribution, the 15.3 in the center. Now, from here, I'm 95% confident the mean amount of product is between 14.4 and 16.17. Well, the assumed to be true population mean, the company is attempting to make products with 16 ounces of stuff in it, or weight, or whatever, vague example. 16 does fall within that confidence interval. So, there is not evidence to reject H sub O. We're not going to accept H sub O. We're not going to accept that there is 16 ounces of product in each item produced, because there might not be. But based on this design with the 5 samples and with the sampling variability yielding us a 15.3, remember, we're looking for evidence against H sub O, and we just simply do not have enough evidence against H sub O to reject it. So, let the assembly line keep producing. What was this going to look like, or what would this look like if you did it with a t distribution or a t-score calculation as opposed to a confidence interval? Let's see. Well, here we have a bell curve set up, and I've set it around 16. didn't intend on doing a bell curve distribution or hadn't thought about it with the previous screen, but I filled it in and noticed that that yellow bell curve was centered around the sample mean because I was going to do a confidence interval to decide whether I was going to reject or fail to reject H sub O. Well, when you do a t distribution or a z-score calculation, t calculation, we are assuming that H sub O is true, and we do make that distribution around the assumed to be true population parameter. So now my distribution, now my bell curve is drawn to be centered around 16, not around 15.3 because I'm not making a confidence interval. So my t distribution is equal to my standardized test statistic is equal to estimate, my sample mean, minus my population parameter, 16, divided by the standard deviation of the estimate. Well, since you're working with means and using the sample's standard deviation, we call that the standard error of the mean. You realize, again, I'm just saying what your formula sheet will say when you take the AP exam. And these little standard deviation formulas are just scattered around, not exactly scattered, or you can find them throughout the multiple pages of that formula sheet, and you just plug them in the appropriate spots. So we get a t-score of negative 2.24. It's negative because our statistic is to the left of the mean, and indeed, you see that my statistic is left to the mean, but I'm not just shading the lower tail, because again, it was a two-sided alternative test. I'm concerned about the item weighing too little or too much, but I can't have something that weighs too little and too much at the same time. That's impossible. You just have to remember that with a two-sided test, you find the area of one tail. Again, the degree of freedom is 4. So, well, I'm getting ahead of myself. You find the area of one tail and you double it. Okay, so you can tell by my work and by the fact that I'm using a chalkboard, I'm a little bit old school. I like to really encourage and enforce the use of the formulas and the tables so students really understand what's going on, and then later, do a calculator lab so they can see how to shortcut the process. So when you go to a DF line of 4, that'll be on the left-hand column of your t distribution table, find that DF line of 4 and go across the body of the table. Now, unlike a z-score distribution chart, the body of the table in a z-score table is all areas under the bell curve. In a t-table, the t-table I use, going across that row, the numbers inside the body are t-scores, not areas under the bell curve. The only place where there's an area is at the top of that chart where it says tail area. So first of all, I'm not going to find a negative t-score, but it's symmetric, so that's okay. So I go across the DF line of 4, and I notice that I have these two t-scores in that chart and not 2.24. So my actual observed t is between the t-score values of 2.1 and 2.8, basically. Well, the tail area for being 2.13 sort of standard deviation, standard errors away from the mean, has a tail area of 0.025, and, that would be 0.05. I changed the order, so probably shouldn't have, because that doesn't tie up. So being this far away from the mean gives me a tail area of 0.05, and being this far away from the mean gives me a tail area of 0.025. So my p-value appears to be between 2.5% and 5%, but it's a two-sided test. This is the tail area, the estimated tail area of that. Multiply it by 2 to account for the two-sided shading, and my p-value is between 5 and 10%. Well, let's not forget my level of significance was predefined at 5%, and my tail area, or my total tail area between the two, is between 5 and 10, implying that my p-value is above 5%. So, since my p-value is greater than 0.05, the predetermined, the given level of significance, we fail to reject H sub O, and well, that's it. That's the relationship between a two-sided test and a confidence interval using a t-score test as a example. I'm Mr. Tarrou. Bam! Go do your homework.